Hello everyone, I'm Shammur of Chowdhury and today I'm going to present our paper, What Does an End-to-End Dialect Identification Model Learn About Non-Dialectal Information? In this paper, we want to study an end-to-end dialect identification model for encoded dialectal and non-dialectal information. Dialect identification is a special case of language identification task where the performance of the model depends on the ability of the model to discriminate between dialects of same language family. So using such model over here, we explored learned internal representation for gender, voice identity, language, channel based characteristics, along with, of course, dialectal properties. But why are we doing this? The end-to-end frameworks gives us a very simplified and flexible training architecture, of course, with improved performance. However, it comes at a cost of blindness. We don't know what information are present inside this network. So in case of speech, we have speaker, language, channel information that impose different characteristics on acoustic signal, making this unwanted signal available to the network. So our revised objective is to study an end-to-end dialect identification model for encoded task-oriented information from non-task-oriented information. So we probe the network for dialectal and non-dialectal information. In this slide, you can see the full experimental flow of our work. On the left, we have a fine-grained ADI model containing 4 CNNs and 2 FCs trained for 17 countries with using shared Arabic as a language. Using Arabic as a shared language. And using this model, we extracted utterance level representation and designed several proxy tasks. But for converting the frame level to utterance level proxy task in the CNNs, we use a simple statistical pooling. So here are our proxy tasks. One includes dialect information that is task oriented, and for non-task oriented information is speaker, language information, and channel information. To design these proxy classifiers and verification models, for classifier, what we did is we took the embeddings, pass it to a simple fully connected layer with softmax as an output layer. So we have a multi-class classification problem for regional and language identification, and gender and channel classification, we did a binary task, and for speaker voice identification, we did a verification task. Then for regarding the regional dialect classification information, we used ADI5 data for classification. The data includes as 5 classes, where 4 describing region-based dialect like Levantine, which includes dialect from Syria, Palestine, then Gulf with Oman, Qatari, among others. We also have another label called Modern Standard Arabic, which we didn't included in this study. So for our task, we selected a balanced class labels for training and test set among these 4 labels. Here we represent our results from our experiment. We actually observed that FC layers encoded the dialectal information unlike the CNNs and is almost near to the results of the ADI-17 model itself when tested on the ADI-5 data. As for our next task, we have on speaker information, mainly gender classification. For this, we use voice celeb data that includes YouTube videos of the celebrities from different profession, age, and then we took a gender balanced data set for classification. From our results, we can see that the network is learning gender information throughout and showing the innateness of this information in the model. Then for finding if in addition to the gender, the model can learn voice identity, we designed our next task as speaker verification task. For this, in addition to VoxCeleb, we use a subset from Common Voice dataset for Russian and Chinese language. Now the task is to take a pair of input signals and then verify if they are from same speaker or not using cosine similarities. So for construction of this verification pair, for VoxCeleb, we use the official verification pair that is being released with the data. For Common Voice, on the other hand, we designed our own pairs using speakers from same gender and a balanced positive and negative samples randomly picked from all the possible samples. Sorry, possible pairs. Now, to compare our findings to a model that learned to recognize voice identity, we designed another network trained on speaker recognition objective using the exactly similar architecture, that is 4 CNN, 2 FCs. And as for the training, we use VoxCeleb dataset that includes 1200 around speakers and 147K utterances. So using this, we see our findings, which we reported in terms of equal error rate. And in here, the homogeneity in the performance per ADI layer indicates, like from CNN1 to FCs, indicates that the model is learning speaker invariant representation in compared to speaker recognition model, which performs significantly well, irrespective of the language we are using. We also noticed another thing, a slight decrease in the EER when we compare CNN4 to FCs, making us wonder if this is due to the capture of vocal information rather than speaker information. So to explore this and to test this hypothesis, we designed our next task as language identification task. We used a subset of common voice data using language like Arabic, English, Spanish, German, French, Russian, and Chinese. And for this study, we again took a balanced data set for training and testing the models. So in this slide, you can see our results from the experiment. We can see that CNN are best capturing language information than FCs, indicating their capability to extract voice representations or voice features. A similar pattern is seen when we did class-wise analysis. So our next and the last task is we classified the channel information of the input signal. For this, we again went back to the ADI5 dataset where the training data was from satellite recording and the dev and test were from high quality archive videos. So we combined this dataset and split into 60-40 for training and testing the proxy classifier. So over here we have our results, which shows that the channel information is present throughout the network, similar to our observation for gender probing. However, unlike gender probing, gender's information were 90 plus, whereas it is on average from 88 to 92, macro F1. So to conclude, in this study, we probed an end-to-end dialect classification model for dialectal and non-dialectal information using proxy classification and verification task, right? So we observed that the dialect information is learned in FC layers. Speaker and speaker gender and channel info is present throughout our network, and the model is learning speaker invariant representation when we tested for voice identity. While we noticed that CNN is capturing vocal representations, this actually helps in tasks like language identification, which also indicates that CNN is mimicking a feature extractor and FCs are more task-oriented layer in this work. Now, this understanding of network for encoded info help us to decide which information can harm the model. For example, the effect of learning channel. We do expect the model to learn dialectal information, of course. gender makes sense. The model didn't learn speaker identity, which is good. So we know that the performance of of a ADI model will be based on its distinguishing capability between the dialects, not because it knows the speaker from beforehand. For language identification makes sense because it is like it is sort of on the same domain of a dialect identification. Actually, dialect identification is a special case of language identification. However, channel is something we didn't, I mean, of course, yes, this information is present, but we didn't want it to be, let's say, from a design perspective. So this understanding of the network for this encoded information we can help us to understand which information can harm the model. For example, as I said, the channel, among others, and this can help us to take better design decision for the intended task. So here I will end our presentation. Thank you so much for giving us time, and hopefully you will see you at QA session. Thank you.